Welcome to the learning series of Tech Topics Thursday. And we're looking at the new basic exam questions that came out July 15th, 2025. We're continuing on with propagation. We're looking at section 7.5 to 7.8 of propagation. These new questions came into effect July 15th, 2025. The actual exam question is on the left-hand side, and the summary and the new question summary is in bold on the right-hand side. Also, what's new for the July 15, 2025 exam is that there's now formulas and block diagrams that you can use. So it comes as a study aid, which you're not allowed to take into the exam, and then the reference material, which you can use on the exam, and that will be provided to you by your examiner. So the difference between the two is that the study aid will give you the formula and then also describes the formula, or gives you a diagram and identifies what the components are. But your reference material just gives you the formula and doesn't give you any explanation. Also gives you the diagram, but nothing's labeled. So section 7 has to do with propagation. Section B, we're going to talk about solar activity, usable frequencies, VHF, UHF, other propagation, and scatter. So solar activity. How do sunspots change the ionization of the atmosphere? So the more sunspots there are, the greater the ionization. So C is the correct answer. How long is the average sunspot cycle? So the sun goes typically on an 11-year cycle. So D is the correct answer, 11 years. What is solar flux? So there is two ways of determining solar activity. One is by the sunspot number, and the second one is by monitoring a radio frequency emitted from the sun, which I think is 10.7 gigahertz. So C is the correct answer, the radio frequency emitted by the sun. And what is the solar flux index? And that would be a measured solar activity that's taken at a specific frequency. So D is the correct answer. What influences all radio communications beyond ground wave and light of sight ranges? And that would be the solar radiation coming from the sun. What effect of the sun's activity influences ionospheric propagation on a daily basis? And that would be the electromagnetic and the particle radiation coming from the sun. So that would be B. When sunspot numbers are high, how is propagation affected? So in this case, it allows frequencies up to 40 megahertz or even higher become usable for long distance communication. So C is the correct answer. All communication frequencies throughout the spectrum are affected by varying degrees by, and that would be A, the sun. So the sun influences the ionosphere, which then influences propagation. So sun is the correct answer. Average duration of a solar cycle is A, 11 years. The ability of the ionosphere to refract high-frequency radio signals depends on the amount of solar radiation. So D is the correct answer. What is the major cause of cyclical changes in HF propagation? And again, that would be due to the solar cycle, which would be C. Now we get into usable frequencies. Observatories probe the ionosphere at vertical incident. What term describes the highest frequency that a region can reflect at the time? And so this would be a signal going straight up and straight down, and that would be the critical frequency C. And that changes from day to day and from time to time. And you can look it up on the website. So that's known as the critical frequency. What causes the maximum usable frequency to vary? So that would be D, the amount of radiation received from the sun. What does the maximum usable frequency mean? So that would be the highest frequency at which the signal will reach a given destination. So remember, the critical frequency is a signal going straight up and down, and the maximum usable frequency would be for any given destination. Here's a new question. Why is communication possible between two continents at a frequency above the local critical frequency? So that would be because the critical frequency goes straight up and down, while the frequency you're currently using goes at an oblique angle. So the signal enters the ionosphere at an oblique inclined angle. So A is the correct answer. What is one way to determine if the maximum usable frequency, MUF, is high enough to support 28 megahertz propagation between your station and Western Europe? So what you can do is you can listen to various beacons that are located around the world, and there happens to be a 10-meter beacon. So you take 300 divided by 28, which gives you roughly 10. So you're looking for something that's around 10 meters. So D is the correct answer. Listen to the 10-meter beacon station, because you want to be close to the frequency that you actually want to use. What usually happens to radio waves when frequency below the maximum usable frequency, MUF, when they are sent into the ionosphere? So they are just bent back to the earth. I mean, that's what you want. If you exceed the maximum usable frequency, then they tend to bounce or go through the ionosphere and not bounce back to the earth. So you want them to come back to the earth. So A is the correct answer. At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours? So a 20-meter band is quite the common band that works most of the time, or nearly all of the time. So C is the correct answer at any point in the solar cycle. Here's a new question. What happens daily when the solar UV radiation increases? So as the solar increases, the maximum usable frequency increases. So C is the correct answer. When is propagation on the 80-meter band generally least effective? And this would be a daytime in the summer. The optimum working frequency provides the best long-range HF communication. Compared with the maximum usable frequency, it is usually so slightly lower. So C is the correct answer. During summertime, which bands are most difficult for communication beyond ground wave? So that would be the 160-meter and the 80-meter band. So B is the correct answer. Okay, now we get into VHF and UHF and other types of propagation. So um, these are a little bit different than skywave and ground wave communication, and these are some special ones that that happen occasionally. Which ionospheric region most affects skywave propagation on the 6 meter band? And that would be known as the E layer. So then you also get a different type of communication known propagation known as tropospheric bending. So what effect does tropospheric bending have on the 2 meter radio wave band? So B, it lets you contact stations further away than normal. What causes tropospheric ducting of radio waves? And that's a difference in temperature. So in the layers in the tropospheric layer, so that would be a temperature inversion. So D is the correct answer. What term describes the portion of the transmitted wave kept close to the Earth's surface due to bending in the atmosphere? And again, that would be the tropospheric wave. A is the correct answer. What is sporadic E communication? So this happens in the E layer, and that's caused by patches of dense ionization in the E layer. So D is the correct answer. For which amateur band is the extended distance propagation effect of sporadic E most often observed? And that's usually at the 6 meter band. So B is the correct answer. In the northern hemisphere, in which direction should a directional antenna be pointed to take maximum advantage of auroral propagation? So here you're looking at the northern lights, and because we're above the equator, you want to point that to the North Pole. So C is the correct answer. Where in the ionosphere does auroral activity occur? So that would be at the E region height. So D would be the correct answer. What analog emission mode is most reliable for auroral propagation? So here you're looking for a signal that's relatively small and still readable, in small in bandwidth and somewhat easy to interpret. So A is the correct answer, CW, because it's readable even when distorted. Um, Excluding enhanced propagation modes, what is the approximate range of normal VHF tropospheric propagation? So this is in the troposphere, so that would be B, 800 kilometers. What effect is responsible for propagating a VHF signal over 800 kilometers? And again, that would be A, tropospheric ducting. Now we get into the section of scatter, and this can happen with any radio signal, usually more prominent at the HF signals. And this is where the signals get scattered and bounce off of different things. So, what kind of unusual HF propagation allows weak signals from the skip zone to be heard? So, that would be the scatter mode D. If you receive a weak distorted signal close to the maximum usable frequency, what type of propagation is probably occurring? So again, that would be scatter. Here's a new question about scatter. What type of VHF, UHF propagation depends upon very small variations in density and water vapor content? So that is based on tropospheric scattering. So D is the correct answer. What makes HF scatter signals often sound distorted? Because energy is scattered into the skip zone through, through several different radio wave paths. So A is the correct answer. Why is HF scatter signals usually weak? And that's because only a small part of the signal energy is scattered into the skip zone. So C is the correct answer. What type of propagation may allow a weak high frequency HF signal to be heard at the distance too far for ground wave propagation, but too near for normal skywave propagation? So again, you're somewhere in the skip zone area, but you're picking up something, and that's because of scatter. You're getting the signal scattered back. On HF bands, when is scatter propagation most likely involved? And that's A, when you receive weak and distorted signals near the maximum usable frequency, MUF. So tropospheric scatter frequency explains VHF, UHF communications well beyond the radio horizon. What makes this propagation mode possible? And again, the correct answer here is A, smaller variations in the properties of the lower atmosphere. And then you can also scatter things off of meteors. So meteor scatter is most effective on what band? So that would be D, 6 meters. A new question. What is the effect of scattering on a radio wave? So, so what happens with scatter is the wave gets redirected in many directions. So B is the correct answer. In which frequency range is meteor scattering most effective for extended range communication? So in the last question, we said it was 6 meter, which is 50 megahertz. So what you need to do here is look for an answer that covers 50 megahertz. So B would be correct. So 30 megahertz to 100 megahertz would be the correct answer. So that's it for propagation. So next week we'll look at the last section, section 8 on interference.